Hi, I'm Sonja Englert. Welcome to my airplane design tutorial number 18. I talked about airplane structural design in the last video, which I thought would be the last one, but I found another worthwhile topic and decided to do another video or two. In this one, I am introducing various forms of airplane drag and how to minimize them to improve performance. Drag is what holds you back from flying as fast as you really want to go. In order to improve the performance and the speed of an airplane with a given engine, the drag must be reduced. Physically, drag, the force that opposes forward movement, is the loss of energy the air loses as it flows around an object. It does not matter if the object moves through the air as in flight, or the air moves around a stationary body as in a wind tunnel. If there was no friction, there would not be drag. In this ideal case, the air flowing around this object with a speed v1 at the leading edge would have the same speed at the trailing edge, without any losses. There would still be pressure on the front end pushing aft, but this would be compensated by equal forces further back pushing forward. But because there always is friction, the air particles stick to the surface of the object and slow down. They lose momentum or energy. This leaves a wake behind the object, a layer of slower air. The pressure on the front end is now only partly compensated. The remaining force that pulls the object back is called drag. There are several different types of drag, which I want to present in some detail because they require different methods to minimize them. The easiest one to understand is form drag. Every object that is moving through the air has to push that air out of the way. How much drag an object produces depends on airspeed, its cross-section, and its drag coefficient. The drag coefficient CD is a number that factors in the shape of the object because that has a big influence on how high the drag is. It quantifies the losses and the size of the wake. As an example, I am using here a flat plate, a round cylinder, and an oval cylinder that all have the same frontal area. The sketch shows the front view that the app is encountering. It looks the same for all three different objects, but in the side view you can see that the shape of the cross-section is different. One is a flat plate perpendicular to the airflow, 2 is a round cylinder, and 3 is an elliptical cylinder with a length to diameter ratio of about 5:1. This chart shows the drag coefficient for the three shapes and the amount of drag the objects would produce if their cross-section area is 3.23 square feet or 0.3 square meter at an airspeed of 90 knots or 167 km per hour or 104 miles per hour. It is easy to see that the flat plate produces way more drag than a more streamlined shape. This information is used on airplanes for lowering the drag by the replacement of round wires or struts with oval ones. By going to a different shape with the same cross-section, the drag can be reduced by up to 80%. The drag coefficient CD of simple shapes can be looked up in tables. For more complicated or optimized shapes like fuselages or airfoils, it is calculated with aerodynamic programs or measured in wind tunnels. Make sure you use the correct cross-section. For fuselages and similar objects, the drag coefficient is referenced to the frontal area, while for airfoils and wings, the drag coefficient is referenced to the chord or wing area. So to minimize drag, first keep the cross-section to the minimum that suits the purpose. Second, streamline the shape to achieve a low drag coefficient. Aerodynamicists spend a lot of time finding the ideal shape for each application that results in the lowest drag, but most of the time, once you have some experience, you can tell by simply looking at it which one of two shapes has lower drag, which in this case is the one on the left. The air is not just getting pushed out of the way, it also has viscosity, which means it sticks to the surface of the object. This causes another form of drag, the skin friction drag. This means that two objects that have the same cross-section but different surface areas can have different drag. The two objects sketched here have the same round cross-section, but shape 1 has more wetted area than shape 2. The wetted area is simply the total surface area of a body. Assuming that the airflow stays attached on both shapes, the second one will have a little less drag. LiDAR designers make use of this. They taper the tail boom down aft of the cockpit, where the volume is not needed anymore. But if the pressure gradient is too steep, the air does not manage to follow the contour anymore and separates from it. The space behind the body is then filled with turbulent airflow, which consumes a lot of energy and causes much higher drag. Obviously, this must be avoided. The skin friction drag is also a function of the Reynolds number. The Reynolds number is the ratio between the airspeed times the length divided by the kinematic viscosity of the air. The latter can be regarded as constant, so only speed and length are the variables. For two objects of different size and speeds, the flow is similar if the Reynolds number is the same, so this number is important for making sure you are comparing apples to apples. To stay with this example for drag comparison, the apples would have to be the same size, but can be of different shapes. Small airplane wing Reynolds numbers are in the range of 2 million to 6 million. Slower flying aircraft with short wing chords like gliders may fly at Reynolds numbers of less than 500,000. If you design an airfoil, it must be suitable for the correct Reynolds number range. That's why model airplane airfoils look different from full-sized airplane airfoils. The flow behaves differently. What this means in a more scientific way is that the friction, or the losses due to air particles sticking to the skin, change with the length of the object. To illustrate this, let's look at airflow blowing over a flat surface at constant speed, so that all the drag is purely friction and there is no form drag. At the leading edge of this flat plate, the air still has its full speed and the energy loss of the particles is high, which means the skin friction coefficient is high. Anything sticking up into the airflow here, like the head of a round rivet, also causes a lot of drag. Further downstream, the slowed down air particles accumulate in what is called a boundary layer, which becomes thicker and thicker towards the rear end of the plate. At first, the slower particles move in an orderly fashion, each in its own little layer according to speed. The boundary layer here is called laminar, and its skin friction coefficient drops rapidly. But there is a point where that breaks down and becomes unstable. The air particles start mixing, the slower ones with the faster ones, and the resulting tiny vortices consume more energy. The skin friction coefficient jumps up again. Once the boundary layer is turbulent, it stays that way, and its thickness is much increased. Further downstream, with increasing thickness, there are less fast air particles reaching the surface of the plate, and the skin friction coefficient drops again. A round rivet head is now submerged in the boundary layer and causes less drag. That's why you can see some metal airplanes with flush riveted wing skins in front of the spar and round head rivets aft of the spar. This basic diagram is valid for airflow around all shapes, but the Reynolds number, where the boundary layer transitions from laminar to turbulent, depends on the shape of the object. For the lowest drag, the boundary layer needs to stay laminar as long as possible to minimize the skin friction drag. The laminar boundary layer is quite stable until the thickest part of the object is reached. It is hard to keep it laminar much beyond that. For that reason, the thickest section of bodies and airfoils is shifted aft as far as practical, where low drag is important during the design stage. Unfortunately, a round rivet head sticking up near the leading edge does not only add drag from its own shape, it also causes the boundary layer to transition prematurely to turbulent. This sketch shows the increase of turbulent, high-friction area caused by an obstacle in the laminar region. Especially on wings, airfoil design that maximizes laminar flow has advanced the laminar region from 20 to 30% of the chord for early airfoils to beyond 90% on the lower surface and more than 60% on the upper surface, thus enabling major performance increases. On the fuselage, design for laminar flow is also important but more difficult to achieve because things like cowlings, doors, windows and other things that would prematurely transition the flow to turbulent. Surface waviness and roughness will also cause the boundary layer to transition to turbulent sooner than a smooth surface, with a corresponding drag increase, which is why the highest performance aircraft use composite materials, which allow much better surface quality than metal surfaces. You can see the result of this when you look at the highly optimized competition gliders. Composite is the only material used there. I will stop the discussion on drag here for now and continue it in my next video with the remaining categories of drag and some performance analysis.